Alright, so let's talk about interference, constructive or destructive interference. So what that means is you'll have two waves of the same frequency and wavelength. Let me just copy this one. Oops. Alright, so here we got two of them that are the same. Right? Now, we can have them, they'll interfere with each other. Like if it's two water waves, you've seen water waves at the beach combine, right? Or sound waves can combine and interfere with each other. So they can interfere constructively or destructively or some way in between. If they're the way that they're lined up right now, this is constructive interference. It almost sounds like a contradiction in terms, right? But it's a constructive interaction. The waves, the dips and such will add up. I know there's a better word for that, whatever. Will add up with each other and make an even stronger wave. Okay, so we'd end up with an even stronger wave, taller wave when they add up, right? However, I can grab one. We can also have destructive interference. That happens in this case. See, where the low point in this wave adds up with the high point in this wave, and they cancel out. And the high point in this wave lines up with the low point in this wave, and they cancel out. And there's anything in between constructive and destructive, but we're just going to talk about completely constructive and completely destructive interference. Okay, so let's think about some conditions here. Two different waves. I want to think about if one travels a different distance than another wave. So if this bottom wave were to travel a different distance, let's say it travels this much further. Okay, I lined it up so that we will have constructive interference still. See how it lines up? Now the best it does with my ability to draw waves. It still lines up there, and I have moved it, see if you can tell, I have moved it by one wavelength. See that? So the path length difference, so this bottom one is traveling a distance of one wavelength farther. The path length difference, d, is one wavelength. Alright? Well, I could also have this thing move two wavelengths. Right? That's the next possible position where the waves line up is if I move it over this far. That's the next possible spot, and that's another wavelength. See that? So now in this condition, I've moved it two wavelengths, and I could move it three wavelengths and four wavelengths. So what we're seeing here is that in order to have constructive interference, if one wave is going to travel a different distance than another wave, with these waves having the same frequency, then the path length difference, that how much farther one wave travels than the other, has to be, oops, that's a 2, a multiple of the wavelength. So I'm putting n where n is 1 or 2 or 3 or whatever you want. Okay, so that's for constructive interference, and that's pretty much it. For some reason, we generally like to speak about frequency instead of wavelength. Well, remember that the velocity of wave is equal to the frequency times the wavelength, right? So if I rearrange this, I can get that a wavelength is equal to velocity divided by frequency, and I plug that in to my d equation here, and I get d equals n v over f. And we also sometimes solve these things for frequency, right? And so we multiply over the f, and I get the frequency would be equal to I would get the frequency is equal to n v over d, like that. And so written like this, it's like I'm looking for different frequencies. So for a given path length difference, d, to find frequencies that will have constructive interference, I plug in different values of n. So I could say frequency number n for a different n, right? Because there will, for any different n that I plug in, I'll get different frequencies, right? So that is the condition we have for constructive interference. Given a certain path length difference, you plug in whichever n you want, and that will be the different frequencies that will have constructive interference at that point. Okay, so let's talk about destructive interference now. Should pretty much be a similar idea. Let's go down a bit. So that was constructive. Alright, so now, let's see, do I still have that? Wave, perfect. Why did that keep happening? Okay, paste a couple of waves on here. And now I want to line them up with destructive interference in mind. Oh, I already did it, really. Okay, so this one might be a little bit trickier. What I did just now is I've moved it a distance of half a wavelength. There, right? Okay, so that's half a wavelength to get it to in that condition. So let's see how much further I have to move it to have it destructive again. That's constructive. That is destructive. So I just moved it another wavelength there. Right, so that total one ends up being, let's see, 3 halves of the wavelength there. And let's try that again just so we know what we're doing. So not that, but that. That's another wavelength. So that ends up being, let's see, so one more wavelength, that's 5 halves of a wavelength. Okay, and so on. So what we're getting here, this one's a little bit trickier, but see, we've always got a half on the bottom, and the other number is 1, 3, 5, and as I continue, I'm going to see that D equals n over 2 times the wavelength, where n is actually odd numbers. 1, 3, 5, and so on. Okay, so now we'll just do the same thing that we did before if we want to write this in terms of frequency. Wavelength is equal to velocity over frequency. Right, so I'll plug that in. So D equals NV over 2F. Multiply the F over, divide the D over, and I get that F, the certain frequency for multiple N, is equal to N times V over 2D. So this is for destructive interference. Alright, so those are your equations, and we'll probably do an example video separately. Alright.